Climate change is obviously giving us global mean warmer temperatures, warm continuing to warm, which means overall humidity goes up, but it's not uniform. So you have regions with too much rain and too little rain. So now we have regions with too little water and too much water, but not in the mean, but seasonally and interannually, and maybe shifts in the baselines as well. So let's look at the next table on adaptation technologies for managing too much water. So adaptation response as before, technologies and descriptions, and as before I'll just read off a couple of points and not read the whole table, which you can go back and do yourself if some particular aspect interests you. And you can see that I cut out the column of link download link here. So too much water requires riverine flood protection upfront. Structural barriers to flooding, dams, dikes, locks and levees are the technologies we are talking about. Flood protection infrastructure used to control river floodwater flow and protect communities against costly effects of inundation. You also have externalities like health related to these inundations, and crop losses, of course. Typically, a permanent construction built at a designated point on a waterway's path to contain water on one side of the barrier. Libya became a big bad poster child for how not to do these. They had built mud and brick dams on a river that actually got hit by a Mediterranean cyclone, which dumped much more water. Maybe a year's worth of rainfall fell in just about 6 hours. Lot of blame put on dams not being maintained, even though it's not clear whether that kind of a rainfall amount could have been handled even if the dam was maintained. Plus, nobody gives them information on such local risks, right? So IPCC provides this so much information, and yet it's not very useful when it comes to making local decisions on particular dams and so on for estimating future risks. So this is going to be critical as well. Optimization of reservoir operations aims to ensure that all planned reservoir objectives are met without compromising those of ecological water requirements. It takes into account a variety of objectives and variables, including cost and revenue considerations of water allocation for various socioeconomic uses. Okay, so there is the too little water and tariffs on water use. Here we are talking about optimization of reservoir operations. Reconnecting rivers with the floodplains. I have a podcast as well on how floodplains have been occupied and creating more vulnerability to floods, more risks of floods, more exposure of people to floods and so on. So floodplains here, reconnecting is always a good idea, good adaptation response to too much water. A green infrastructure approach that focuses on removing barriers along the edges of the river. This allows the river to re-establish its natural course over time, eventually connecting to its historical floodplain or creating a new one. It can include removal or setting back of levees, raising of a deeply engraved riverbed, or expanding a river's bank. As an adaptation response, this could be good cost investment for longer term benefits, but obviously implementing it requires all the things we talked about before in terms of mainstreaming these into the fiscal policies and budgeting and so on. Riverine flood protection. So this is the same topic as before. Flow-through dams, also known as perforated dams. So dams constructed solely for the purpose of flood control and mitigation of flood risks in downstream communities and ecosystems. Accommodation of flooding, so flexible buildings and infrastructure. Elevated houses, etc. Design of infrastructure that can withstand the impact of flooding events, resulting in minimizing socioeconomic damages and effective climate change adaptation. So we talked before about acceptable risks and unacceptable risks. So private developers can provide these kind of infrastructure for bridges, roads, and developers can also build houses to manage these flooding, let's say frequent flooding expected But if you get hit by a hurricane or an earthquake, then obviously that responsibility may end up lying with the government as acceptable risk. Okay, ecological river restoration, so nature-based solution kind of approach, involves ecological, spatial, and physical management practices to, again I have included this here, but nonetheless, involves ecological, spatial, and physical management practices to return a river back or close to its natural state. Common restoration techniques include reconnecting rivers with floodplains, re-establishment of the river meandering form with no barriers along its banks, and stabilizing surrounding soil to reduce sedimentation and erosion. Obviously, developers are always looking to put people on the river banks or lakes. High property prices, they want to make profit and get out, but it's not always easy to move people back or even to make legislation zoning to keep people far enough away from floodplains and riverbanks and so on. So it's always a battle. Multipurpose dams, dams that combine two or more functions of traditional single-purpose dams into one hydro infrastructure project. You can read more about that there. Zoning and land development limitations that I just mentioned. This approach divides urban areas into zones with varying degrees of development restrictions depending on flood risk level. So you have to have a map of the flood risk, and it's non-stationary because with climate change you are getting alterations to flood risks and vulnerabilities and exposures. Constructions or reconstruction is often prohibited in high-risk areas, for example floodplains, while in other areas restricted development is permitted given certain building regulations are followed. Of course, risk maps are needed here. Looking at urban stormwater management now, urban green spaces we mentioned before. Green spaces are areas covered by vegetation such as grass, bushes or trees. Urban settings, they help to uptake and infiltrate water, decreasing runoff rates, which also often contain excessive amounts of pollutants. A few more details there. Permeable pavements and parking lots. We mentioned this before in another podcast. Infrastructure designed in urban settings to facilitate stormwater runoff and mitigate urban flooding and stormwater overflow risks. Built to utilize ecosystem services provided by soil, allowing water capture and infiltration. More details there. Bioswales, again a nice adaptation response we mentioned before. Strips of vegetated areas that redirect and filter stormwater before being released into the ocean, for example. Typical bioswale is a long linear strip of vegetation in an urban setting used to collect runoff water from large impermeable surfaces such as roads and parking lots. Okay. Optimization of urban drainage systems improves existing drainage systems. Computer simulation models improve real-time operations using algorithms to evaluate system performance, reveal deficiencies, identify high flood risk areas, and illustrate optimal design improvement interventions such as optimal pump capacities, storage sizes, locations, and green spaces, etc. So combining early warnings with these, so crisis management, disaster preparedness and disaster recovery, as well as resilience building, all have to work together. Runoff control structures to temporarily store water. So this is critical. Structures designed to capture runoff during peak flows and can function as temporary storage sites, typically built with a discharge component to slowly increase water into nearby waterways to avoid it overflowing from storage basin. So you have many times situations like in Kerala 2018, I think also 2020, when you have massive floods, all the water runs off because you don't have such structures, adaptation responses, and then the rainfall disappears for the next few weeks or even months. Then despite the heavy rain, seasonal total may look great, but the distribution is such that you end up with a drought or water shortage. Okay. Finally, under this, too much water, glacier lake outburst prevention, artificial lowering of glacial lakes is technology. The process of draining water from glacial lakes vulnerable to overflow by digging a canal from the lake to a nearby river. Drainage reduces water level and decreases pressure on moraine dams. Moraines are the debris that are pushed by the glacier and left, which act as a dam, natural dam, And when a glacier breaks down and outburst happens, then these moraine dams may get washed out. So you want to use drainage reduction to decrease pressure on the moraine dams. This in turn reduces the risk of burst events. These are low frequency, high impact events that we definitely want to be prepared for. Okay, I'll leave this here and we'll come back and look at adaptation technologies for water pollution. So the table we saw in the beginning, we are slowly covering each component. This one is a bit shorter, but that's fine. Still about 10.5 minutes. So see you in the next podcast. Okay.